Welcome everyone. My name is Saksham Bansal. Today we are going to explore the core components that make things move in the world of electronics and robotics, motors and servos. Our goal is to go beyond the basics and give you a solid understanding of how they work, why they are different, and how can you control them for your own projects. There are three main types of motors you'll encounter in hobbyist and professional robotics. DC motor, our simplest, designed for high speed, continuous rotation, think of wheels or fans. Stepper motors move in precise, repeatable steps, which is great for things like 3D printers and CNC machines. Servo motors are designed to move to a specific angle and hold that position with precision. Today, we are going to focus on two most common for general robotics: servos and DC motors. So, what exactly is a servo? It's not just a motor, it's a complete system in a box. Inside, you have a DC motor, a gearbox for torque, a potentiometer that acts as a position sensor, and a control circuit. This is a closed loop system. It knows what position it's at, and it constantly tries to correct itself to match the angle you command. This is why servos are perfect for things that require precision, like robot arms and steerings. We control a servo's position using pulse width modulation, PWM. We send a pulse every 20 milliseconds. The width of that pulse tells the servo where to go. A 1 millisecond pulse typically goes to 0 degrees. A 1.5 millisecond pulse means go to the center or 90 degrees. A 2 millisecond pulse means go to 180 degrees. The servo's internal circuit measures this pulse width and derives the internal DC motor until the potentiometer reports that it has reached the correct angle. Okay, let's get hands on. We'll wire up a servo. It's just three connections. The brown wire goes to the ground. The red wire goes to 5-volt pin, and the orange signal wire connects to the digital pin 9. Now for the code. The Arduino's servo.h library makes this easy. Include servo.h brings all necessary functions. My servo.attach tells the program a servo is on pin 9. My servo write is a key command. It automatically generates the correct PWM pulse for the angle you give it. Let's upload this and see it in action. Now, let's switch gears to DC motors. Unlike servos, these are simple, open loop systems. They have two main parts: a stationary magnet called the stator and rotating coil of wire called the armature. When you pass current through the armature, it becomes an electromagnet, and the magnetic force between it and the stator creates torque, causing it to spin. More voltage generally means more speed. So, why can't we just connect a motor directly to an Arduino pin? There are two main reasons to it. Too much current. Motor draws far more current than an Arduino pin can safely supply. This would damage your Arduino. Second, there is no direction control. An Arduino pin can only be high or low. We have no way to reverse the polarity to make the motor spin backwards. To solve this, we need a special component called a motor driver. This is an H-bridge motor driver. The best way to think of it is as a 4 electronically controlled switches surrounding the motor. By closing different pair of switches, we can change the direction the current flows through the motor, which changes the direction it spins. It also allows us to power the motor from a separate, more powerful battery protecting our Arduino. This wiring is a bit more involved, so let's do it step by step. The key is to power the H-bridge with your external battery, and then connect the control pins from the Arduino. And most importantly, you must connect the ground of the battery to the ground of the Arduino. Okay, let's look at the code that makes the H-bridge work. At first glance, It might seem more complex than the servo code, but it's actually very straightforward once you understand the three main commands. First, just like before, we define our pins to make the code readable. We have our two direction pins, in one pin and in two pin, connected to pins 7 and 6. Then we have a speed control pin, enable pin connected to pin 5, which is a PWM pin. Now, inside our loop, you can see the pattern. To make this motor spin forward, we set the in one pin to high and in two pin to low. Think of this as opening one gate and closing another to direct the flow of electricity. Then, to control the speed, we use the analog write command on our enable pin. Analog write sends a PWM signal just like the servo to rapidly switch the motor on and off. A value of 255 means the motor is on 100% of the time. Full speed. A value of 127, as you can see in the backward section, means it's in half of the time, so it runs half the speed. To go backwards, we simply reverse the direction pins. We set in one pin to low and in two pin to high. This flips the direction of current through the motor, making it spin the other way. And to stop the motor, we set both direction pins to low. This effectively cuts the power and breaks the motor. So, go ahead and upload this code. You should see your motor spin forward, stop, and spin backwards at slower speed, then stop again, repeating the cycle. So, to recap, use a servo when you need a precise position control, like a robotic arm or steering. Use a DC motor when you need high speed, continuous rotation, like for the wheels of the robot or the fan. Servos have a built-in control and feedback. DC motors are simpler but require an external driver like a edge bridge. Finally, a few key rules to remember. Always use an external power supply for your motors. Never power them directly from the Arduino's 5-volt pin. Always connect the grounds. Your motor supply, ground, and Arduino ground must be connected. Start simple. Get one component working before adding more complexity. This will save your hours of troubleshooting. That's our deep dive into motors and servos. I hope this gives you a strong foundation for your future projects. Thank you, and I'm happy to answer any questions.